So, today's topic for our lecture is related to a phase diagram. One of the most important objective of engineering metallurgy is to determine the properties of material. Okay, when we know the properties, then only we work on that material. So, properties determination is very important. Next, the properties of material is a function of the microstructure, which depends on the overall composition and variable such as pressure and temperature. Okay, the property change as temperature changes, and also the property changes as pressure changes. Hence, to determine the phase present in the material system, an equilibrium or phase diagram is plotted. So, to change the phase or to see the changes in phases, so equilibrium phase diagram is very important. So, it is required to plot. Equilibrium diagram or phase diagram is a graphical representation of various phase present in material system at various temperature and composition point. Okay, so temperature is very important. At various temperatures, what are the different phases available and what is the composition present at that temperature? That is very important. All the phase diagram have temperature as the ordinate, that is y-axis, and percentage composition by weight as the x-axis, that is also called as abscissa. Okay, so on y-axis, temperature is there. On x-axis, percentage composition by weight is there. If we see the uses of equilibrium or phase diagram, the equilibrium diagram is used to obtain the following information. First information is it shows the various phase present at different composition and temperature. Okay, so different phases are present at different composition and temperature, and it is important to look these conditions by using the phase diagram. This is the one application. Second, it indicates the solid solubility of one element in other, whether it is soluble or that solid soluble in elements or not. That is also shown by using this diagram. Third point, it shows the temperature range over which solidification or liquidification of material system occurs. The range becomes minimum to maximum. In between that, how much the temperature range is available, that is called as temperature range. Okay, so if we consider the range is 15 degrees Celsius, so 0 degrees Celsius is minimum and 15 degrees Celsius is maximum. So 15 minus 0, this is the range present in that condition. It indicates the temperature at which different phase start to melt. Okay, so at different temperature, different phases gets changes or melting it starts. If we see the basic terms, first term is system. The substances that isolate and unaffected by their surrounding are known as a system. The substances that isolated and unaffected by their surroundings are known as a system. It may be composition of solid, liquid, gases, or the combination, and may have metals and non-metals separately or in any combination. A system is capable of changing its composition, temperature, pressure, density, etc. If we see the phases, it is a physically and chemically composition of a substance, that is system, separated from the other portion by a surface and interface. Each portion have different composition and properties. In an equilibrium diagram, liquid is one phase and solid solution is another phase. Third point is variables. A particular phase exists under various conditions of pressure and temperature and composition. These parameters are known as variables of the phase. If we see the basic terms, that is component, these are the substances or elements or chemical compound whose presence is necessary and sufficient to make a system. A pure metal is one component system, whereas an alloy of metal is a two component or binary system, etc. Fifth point is alloy. It is a mixture of two or more elements having metallic properties. In the mixture, metal is in the large proportion and the other can be metal and non-metals. Gibbs phase rule. Gibbs phase rule establishes the relation between the number of variable, that is F, the number of element, that is C, and the number of phases, P. It is expressed mathematically as follows. P is equal to P plus F, that is number of phases plus number of variables, is equal to number of element, that is C, plus 2. This is equation number 1, where P is number of phases in system, F is number of variables that can be changed independently without affecting number of phases, C is number of elements, 2, it represent any two variables amongst temperature, pressure and composition. Out of that 3, may any two present here. In general, all equilibrium diagram studied at constant pressure, hence Gibbs phase rule is modified to P plus F is equal to C plus 1, equation number 2. Phase rule helps to determine maximum number of phase present in an alloy system under equilibrium conditions at any point in phase diagram. The phase rule can also be used to determine the degree of freedom that can be changed. Gives free energy for thermodynamic stability of phases. Gives free energy for thermodynamic stability of phases describes the amount of energy that released or consumed when a phase is created from the other phase. Okay, how much energy gets consumed or released, that is important. So it is taken by this. Gives free energy of formation, that is delta GF is relative value, allows us to compare energies of different phases. So by the conventions, the value of delta GF for pure metal or element is assumed 0. The phase having lowest value of Gibbs phase energy is a stable phase. If we see Gibbs free energy for thermodynamic stability of phases, Gibbs free energy of any phase varies with the pressure and temperature. The fundamental relation between them is given as follows. G is equal to E plus PV minus TS, where G is called as Gibbs phase energy in joules per mole, E is internal energy in joules per mole, P is pressure in Pascal, V is volume in centimeter cube per mole, T is temperature in degrees, and S is entropy joules per degree mole. At high temperature, phase with high entropy are very stable because TS term in equation has negative sign. Similarly, at high pressure, phase with high volume are unstable because PV term has positive sign. The Gibbs free energy tells us whether a reaction will take place or not. The next point is solid solution and compound. The element present in the alloy in the largest portion is referred as base metal or parent metal or solvent, and the other element are referred as alloying element or solute. Okay, if we consider one solution and if we mix two different elements in that solution, then if the quantity of the solution becomes less, that is called as solute, and if the quantity is more in number, then that quantity is called as solvent. Solid solution is a type of alloy in which the atoms of alloying elements are distributed in the base metal and both have similar crystal structures. The composition of alloying element may vary, but the structure should be similar to base metal. If we see the types of solid solution, then two different types are there: substitutional solid solution and interstitial solid solution. If we consider the substitutional solid solution, there are again two different types, that is regular or ordered substitutional solid solution and random or disordered substitutional solid solutions. If we consider substitutional solid solution, in substitutional solid solution, atoms of alloying element occupy the atomic size of base metal. They are further classified as A point, regular or ordered substitutional solid solution. In this type, the substitution of atoms of alloying elements in definite order in the base metal matrix. Example, nickel aluminum solid solution below 100 degrees Celsius. Okay, so if we consider order substitutional solid solution, this is nickel aluminum condition. Element replaces host atoms in an orderly arrangement. Okay, if we consider this white color circle, that becomes nickel and that is called as solvent, and this red color atom becomes aluminum, and that is less in number or less in size, so it is called as solute. Second type is random or disordered substitutional solid solution. In this type, substitution of alloying elements is in any random order in the base metal matrix. Example is alpha brass, that is randomly present. If we consider this is white color is copper solvent and zinc is solute. Okay, it occupies this place randomly. Second type is interstitial solid solution. In interstitial solid solution, the atoms of alloying elements occupy the interstitial site of base metal. This is called as interstitial sites. So in that interstitial site, the different elements occupy. Okay, here carbon occupies that interstitial sites in iron or solvent. This type of solution is formed when atomic size of alloying element is much smaller compared to that of the base metal. For example, iron, carbon. Okay, then Hume-Rothery's rule for solid solubility. According to Hume-Rothery, solid solution is an alloy of two or more element wherein the atomic crystal structure of alloying element, that is solute, is same as that of base metal matrix. It's called as solvent. The solubility limit of the solute in the solvent of the alloying element in the base metal matrix is governed by certain factors. These governing factors are known as Hume-Rothery's rule for solid solubility. These governing factors are as follows. First is atomic size. Alloying elements having similar atomic size as that of base metal matrix have better solid solubility. Next is for a favorable solid solution formation, the difference of atomic size of solute and solvent should be less than 15%. Chemical affinity, element having lower chemical affinity have greater solid solubility. Element having higher chemical affinity have the tendency of formation of compound and hence restrict the formation of solid solution. In general, the alloying elements located closer in the periodic table have higher solute solubility. Third point is relative valency. Metals having lower valency have more solubility for metals having higher valency. Hence, for better solubility, the base metal selected should be one that has lower valency as compared to that of alloying elements. Fourth point is crystal structure. As mentioned earlier, solid solution is an alloy of element having similar crystal structure. Difference in crystal structure limits the solid solubility of elements. Okay, so today we stop here, and today we see the point that is Hume-Rothery rules for solubility, then types like solid solution and compound, then gives free energy for thermodynamic stability of phases, then gives phase rule. We already learned this. Then basic terms, and uses of equilibrium phase diagram, and introduction. Okay, so thank you.